Right, now, let's talk a little bit about precession, because we've talked about the celestial sphere, right? And the celestial sphere has this north celestial pole, and we have the pole star Polaris near the north celestial pole right now. But that's actually going to change, because Earth is spinning, and it's being affected by the gravitational pull of the sun, and it's going to wobble, just like a top wobbles. You know, if you spin a toy top, you notice its axis wobbles. That's called precession. And the precession of the axis of a spinning top is due to Earth's gravity, but the precession of Earth's spin axis is actually due to the sun's gravity. And so what this means is that the plane of Earth's orbit, the plane of Earth's spin, is perpendicular to the spin axis itself. So all of the celestial coordinates are actually going to move around, including the line of nodes, which is going to change when eclipse season actually occurs. It's a very long cycle, 26,000 years, and so in about 26,000 years we'll be back to having Polaris as the pole star as it is right now. Down here we have the cycle that's just starting, because this is where we're at right now in the cycle, and it's going to move like this as Earth's axis actually processes around and points to these different stars just like a giant spinning top. So this actually leads to a change in our whole celestial coordinate system. And if we look back a few thousand years, we actually see evidence that the pole star was different. Like in the time of the Egyptians, 3,000 years ago, say, we had a different pole star, and that's a historical fact. Yeah. Okay, so now we're really getting to chapter 2, centric method. All right, so we have the basic idea here is that the beginning of astronomy is kind of the beginning of critical scientific thought in general. And the Earth was, of course, historically going through religious accounts and things like that. The Earth was thought to be the center of everything. And there was a good kind of religious reason for doing that, because placing Earth at the center placed man at the center, which also made any religion central, which increases the influence of a church body. So there's kind of a built-in reason why society should want to have man at the center of things, because it makes societal constructs of all types more important and gives them more power. So we've been around for millions of years, and for millions of years, presumably man thought that Earth was actually the center of everything. And it kind of looks that way. If you look out at the sky, you see the stars, seemingly spinning around us, and rising east and setting to the west. It looks like we're actually at the center. So the scientific revolution is very recent in human history, and only a few thousand years ago, the seeds of this began in the time of the ancient Greeks, and the scientific method then sort of begins in that time, but we're going to see that it didn't really form in the modern pattern. A kind of the scientific method itself, you might say, was developed scientifically. It's kind of a weird way of looking at it, but it didn't just come out in whole cloth. It's sort of little pieces of the scientific method were in place in the time of the Greeks, but not everything that we now consider part of the scientific method. Let's see, what happened when they did that? Oh, yeah. Okay, that's this is Stonehenge, of course. How many people have been to Stonehenge? How many people haven't been to Stonehenge? Worked out perfectly. Gotta be one or the other. Okay. Well, anyway, this here is Stonehenge, and this is actually a shot that this is like really, really old now, but I bought my son this little camera light, which was really cool back in the day when there weren't cell phone cameras, basically. So he was going around Europe. One time we went to Europe, and he got a shot of Stonehenge on a Druid-friendly day. A lot of days and this and stuff like that. Kind of cool. Oh, my daughter was fascinated by the fact that my camcorder stopped working, so I have no video of that visit. And that's supposed to go with the whole eerie thing going on there. There's a lot of weird things that happen there. That's a vegetarian sandwich that my son also took a shot of. It's like the color. That's Big Ben. That's been destroyed more times than you can imagine. That thing just keeps blowing up and get rebuilt. Anytime there's a disaster in England, that's the first record. They always really do a good job destroying it. And that's the actual tower, I think. World Report. This is the medicine wheel, which is kind of a Native American historical observatory, we would think of this as, because the different spokes here could be used to establish the times appropriate for planting crops and things like that. Because you can see the sun rise in different spoke directions, and because of the motion of the sun on the ecliptic, you actually could recognize a particular direction as being the time when planting would be appropriate. And this is a Mayan, observatory. So, seen better times. But this is a pretty sophisticated structure with a lot of alignment slots and holes that you could look through, again, so that different astronomical types of alignments would be significant for religious reasons or maybe for agricultural reasons. And this is a mosaic from Persia, which shows a lot of astronomical or astrologically related people doing their thing here. And we actually know a little bit more about what was actually being discussed at the time. A little bit of an argument about religious services, and actually I always thought it was some kind of instrument, but we see what it actually is. Apologies for this, by the way, it gets a little worse. It gets worse before it gets better. So anyway, this is weird. This is a stretch. That's actually because did you notice Phelps showed up in the head of Orion, that thing? It's kind of, this is actually a thread. Okay, and they are related because they both swim. Okay. All right, so the scientific method. If we look back to the ancient Greeks, then we see that they actually didn't see much of a connection between, say, mathematics and the real world. They were into mathematics and geometry and all that stuff, but they actually didn't really find too much of a direct connection between mathematics and the real world, because the real world was considered to be not ideal. I mean, there was all kinds of non-ideal things going on in the world, like storms and death and disease and wars and things like that. But the ideal universe was purely mathematical, ran by mathematical laws. But they didn't see any connection between the two. So we have this perfect mathematics kind of governing what happens in the sky with astronomical objects. Perfect things like the sun and the moon, but had no connection with anything going on Earth. So there was kind of the beginning of logical thought, but nothing like science applied on Earth at that time. So that's why I said you kind of see the seeds of the scientific method or some kind of scientific thought, but not anything like modern science. So the imperfect reality was, there wasn't any point in even making observations of it. It was not mathematically perfect. Who cared about what's going on Earth? But this changed with Aristotle, who actually started to use the scientific method in a limited way in certain applications, and actually started to bring some of these concepts of an ideal universe to bear on the Earth. So we have time running backwards here, of course, because he was born in 384 BC, died in 322 BC. So I remember that time period. We'll talk about a few other important Greek thinkers and how they put together chronologically. So we have this idea of observation, theory, prediction, and testing. Okay, so Aristotle makes an observation. Of course, they're aware of eclipses. And during a lunar eclipse, we see the shadow of the Earth moving across the face of the moon. But he noticed it wasn't just a flat line, straight line coming in, like a sheet of paper was moving. It was curved. So he deduced that the Earth would be round. So he deduces that the Earth must be round. In fact, he deduces it must be spherical. He doesn't think it's a disk or something like that. He thinks it's spherical. And if it's spherical, then that means that as you move through latitudes, you should see stars change their height above the horizon, just as we do with the North Star. Look at the North Star. We see the North Star at about 45 degrees above the horizon in Fairfax, as we are. But if we go north, the North Star actually rises up until it's at the zenith of the North Pole. And if you go down to the equator, it drops down to the horizon. So he deduced that that would have to be true as we change our latitude, moving along north and south on the Earth. And of course, this was confirmed, because if you go out on a sailing ship or something like that and you move around, you're actually going to see the stars change their altitudes up the horizon. And that's completely consistent with motion on a sphere, a spherical shaped Earth. So we still have, I guess, a flat Earth society. But even already at that time, it was deduced that the Earth actually was round by Aristotle. So we sort of consider him the father of the scientific method. Eratosthenes. Now remember the way the time is sequencing here. We have Aristotle 384 BC to 322 BC. And so a little bit later than that, actually after Aristotle was dead, we have Eratosthenes born 276 BC. He wants to use Aristotle's geometrical idea of the spherical shape of the Earth to actually measure the diameter of the Earth, if he can do it. So he does this in a very clever geometrical way, because he knows that there's a certain well in Syene, Egypt, where the sun is exactly overhead on June 22nd of any given year. And the reason that we know that is because the well is very deep. When you look in the well on June 22nd, you're blinded by the reflection of the sun. And it's a deep well, and wells tend to run straight down along a radial trajectory toward the center of the Earth. So basically this means that on June 22nd, the sun is straight out a radial trajectory from this point in Egypt. So knowing that, he went to a different city. He went to Alexandria and measured the angle between the sun and the actual zenith point, which is a straight overhead point. And then we'll see how he put together a geometrical argument to actually determine what the radius of the Earth is. Well, one thing you have to know is the distance between the two cities involved, between Syene and Alexandria, is about 5,000 stadia, which are units that are about a third of a kilometer roughly. Okay, so next we're going to go through a little diagram here of how this argument is done. Okay, so we have the Earth there, and we have Syene. Now Syene is where the well is. So on June 22nd, the light from the sun goes straight down to the well, which is not very deep. Because it does, but the point is that the sun is straight over that point on the Earth. So we have a straight line going up to the sun along here. Now Alexandria, we can measure the angle between the zenith, which is the straight out point from the center of the Earth to that point. We can measure the angle between the zenith and the actual sun itself, which is at the end of these sun gates that we're looking at. That angle is the angle that turns out to be 7.2 degrees. So far, he's developing an argument. He knows that this angle is 7.2 degrees because he measured it. He also knows the Earth is round because of the work of Aristotle. So that means that if you remember how geometry works, all these yellow lines are parallel. So that's an exterior angle would have to be the same as this angle down here. So now this leads into this really interesting discovery that the angle measured from the center of the Earth between Syene and Alexandria is 7.2 degrees. That's his whole reason for observing the sun. He's really trying to get that angle. Because if you know that angle, and you know the actual distance between Alexandria and Syene, 5,000 stadia, you can use a simple proportionality argument to derive the circumference of the Earth.